Okie dokie, we have 14.15. We're given that the point of a needle moves in simple harmonic motion with a frequency of 2.5 hertz. So let's just go ahead and write that down up here. We have 2.5 hertz. We're going to want to remember that for later. And we know that at t is equal to 0, so our starting point, we have that our position x is equal to positive 1.1 centimeters. And at that point, the velocity is negative 15 centimeters per second. Alright, so the first part of the problem is to find the acceleration at t is equal to 0. And this one kind of gets a little bit fun. So, let me see here. So we have that our angular acceleration, since this is moving in simple harmonic motion, we're going to need to tie in our angular acceleration to find this. So we know that that is equal to 2 pi times our frequency, which we're given in the problem. And that comes out to be 15.71 radians per second. And then we know that our acceleration, just from equations given in the book, is equal to the square root of our starting position squared plus our starting velocity squared over our angular acceleration squared. Alrighty, so then basically at this point now, since we have our angular acceleration, we can just plug and chug. And you can convert these centimeters to meters, but we're dealing with the acceleration of a needle. So we're just going to keep it in centimeters for this problem. So we have that our starting position is at 1.1 centimeters squared plus our starting velocity, which is negative 15 centimeters squared, over our angular acceleration, which is 15.71 radians per second squared. So then we go through that, 21 plus 246.5. Alrighty, so then we go ahead and plug through all that wonderful math there, and that's going to come out to be 146 centimeters Alright, that's our amplitude. For some reason I was thinking it was going to be the period. But yeah, so our amplitude is simply 146 centimeters. Or if you want to be, conventional, it's just 1.46 times 10 to the negative 2 meters as our amplitude. That's the greatest displacement from rest that this needle is going to undergo. So then, part B asks us to write equations for the position, velocity, and acceleration. So we're not asked to actually solve anything. We're just asked to set it up so that we can find it at any given time. So we know that the standard form for position in simple harmonic motion is our amplitude times the cosine of our angular velocity times our time plus phi. And we'll get into phi here in a second. So we know our amplitude from the previous problem is 146 centimeters times the cosine. And then Here we also know our angular acceleration is 15.7. We'll just round that up from 7.1 times our time. And for the first part of the problem at t0, this is just going to be phi. But at any other time, we'll be able to find the position because that's going to be our one unknown variable. And phi, we have to actually find phi. I forgot to do that at the start. So we know that tangent of phi is equal to negative, and this is an equation from the book, negative starting velocity times our starting position, negative starting velocity over our angular acceleration times our starting position. So now we know that phi is equal to a tan, or arctangent, of the negative starting velocity in the x direction times our angular velocity times the start. And we have all these from the problem itself and from our from part A when we found the angular velocity. So we do that math, and that's going to come out to be 0.72 0.72 radians. And we want to put that in radians because our angular velocity is radians per second. This does originally come out as being 40 degrees, but again, we want it in radians. So anyway, so that is just going to be plus 0.72 radians. And then the kind of a fun thing to remember is that velocity is equal to the derivative of your distance. So if you don't want to have to remember that your velocity is equal to the negative angular velocity times your amplitude times the sine of your angular velocity times time plus phi, you can just simply remember the equation for position and take the derivative of it to find your velocity. And we can go through that here. Just from chain rule, we know that if you have a function inside of a function, you take the derivative of the function and put it on the outside and multiply it to the original function. So we have the derivative of our angular velocity times time. Since we know our angular velocity, the variable here is going to be the time. So that's just going to be our angular velocity, the constant, plus effectively 0, since phi again is known. It's not a variable. So the derivative of a constant is 0. Times our amplitude, and then the derivative of cosine is negative sine. And that's where this negative here comes from. And then we just have the original function inside the parentheses. And then that just comes, you can write that simply as negative blah 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 blah. But anyway, so there's that for you if you want it. So now we can just plug and chug everything in. We have our negative angular velocity here, which is 15.7, times our amplitude, which is 146, times sine of, again, our angular velocity times the time elapsed, plus our 0.72 radians. And then we just kind of simplify everything that we can, and that's going to come out to be 229 times the sine, negative 229, times 15.7 times t plus 0.72. And then for acceleration, we kind of have the same deal for finding the acceleration. We can just take the derivative of our velocity, or the second derivative of position. And we can go ahead and go through that again. So we have that our velocity is equal to sine plus phi. Alright, so to take the acceleration is equal to v prime, or the derivative of velocity, we again just do the same thing that we did before, where we use the chain rule. So with chain rule, again, we just take the derivative of our inside function times our outside function, times the derivative of our outside function. So we can just look at our outside function here as a negative constant, because again, these are known, times the sine of theta. And then we'll do the chain rule part here in a second. So from that, we have the derivative of sine is cosine, but we have a negative out here again. So that's going to be negative constant times our cosine of theta. And then from the chain rule part here, again, we just take the derivative of this, with which the addition rule, that's just going to be the derivative of both of these. And since phi is a constant, that's just 0. And so the derivative of this term here is just the angular velocity. So that is just going to be times the angular velocity. And then we expand this back out. Our constant is negative angular velocity times our amplitude times the cosine of our inside function times angular velocity. And that gives us our negative angular velocity squared times our amplitude times the cosine of our angular velocity times time plus phi. Alright, so now we're ready to just plug our known values into this equation to get the general equation for acceleration. So we know that our angular velocity, oh boy, is 15.7 squared times our amplitude, which is 146 centimeters, times the cosine of our angular velocity, which is 15.7 times t plus phi, which is 0.7. And then we just, simplify everything that we can, and that's going to come out to be 3.46 meters per second squared times the cosine of this, because I don't have room to write it.